This video is over topic 9, number 1 through 3, looking at per capita and scaling. So per capita is always going to be the amount of whatever it is you're talking about divided by the number of people. So per capita amount to be cut is going to be the total amount cut divided by the number of people. So we have here 50 billion. So it's important to include that as part of the amount there. It's not just 50. 50 billion divided by 340 million. And there's lots of ways you could adjust, but you do need to make sure to account for that billion and million. You could write this out fully in standard form. You just have to do a lot of counting zeros, making sure you do that correctly as you do the calculation. You could use scientific notation and do it, or not necessarily scientific notation, but use the power of 10. So billion is 10 to the 9th, and million is 10 to the 6th. You could go all the way and go to correct scientific notation. It would be 5 times 10 to the 10th, and 3.4 times 10 to the 8th. You could also adjust, just do like that level type of adjustment. So you could have 50 billion and just go down a level. Adding 3 zeros would be 50,000 million, and then 340 million. So once those match, they can cancel. If you do write it out with zeros, you can cancel out, like match, like as long as you have a zero on top, zero on bottom, they can cancel out. So that's also something that can be helpful. You could also go the other way, 50 billion, and change the 340 million to maybe the decimal 3 places, 0.34 billion, and then the billions would cancel. So lots of different ways to approach doing this calculation. If you did it, this would be 50 divided by 340, and it would be times 10 to the 9 minus 6. So you get something times 10 to the 3rd, and then you'd adjust accordingly. This would be 5.34 times 10 to the 10 minus 8. 50 divided by 340 is 0.147. Goes on a while. The third, 5 divided by 3.4. It's going to be similar, but it's 1.47. So just decimal point moved over 1 times 10 squared. It comes out then, however you approach that calculation, you should end up with 147. So 147, and putting that into a sentence, that's dollars per person. Or you might more naturally say for each person or every person, this government is cutting $147 per person. So with large amounts that you're doing per capita, the result is going to come out as like more than one thing per person, more than $1 per person, because there was more dollars than people. But we did have to do that millions and billions adjusting. In other cases, we have, again, I'm scrolling through the scaling. You can look at that on your own time. But looking at number 2 here, where we are looking at the per capita for something where there are much more people than there are the items. So when we do the division of the number of things, in this case, the number of Walgreens divided by the number of people, we're going to get a very tiny number. So we have 188 Walgreens in Indiana, 224 in Michigan. But if we want to talk about does Michigan have more Walgreens than Indiana? Well, Michigan is a bigger state, it's a larger area, it is more people. So, do they actually have more Walgreens if we adjust that for the population? So, for that, we need to know the population. So, Indiana, 6.8 million, Michigan is 10.1 million. We're going to calculate the Walgreens per capita rounded to 7 decimal places. So, for Indiana, that's 188 divided by, and for the 6.8 million, I'm just going to go ahead and write that out in standard form. So 6 comma 800,000 for the 6 million there. 6.8 million. Pause for a second. Okay, so 188 divided by 6.8 million. And depending on your calculator, that may come out, it may give you the decimal form, which is 0.000027 6 followed by a 4, so it rounds down to 6. It might give you something that looks like this and it keeps going on, but if you look at the end, it might have an e minus 5 or a 10 to the negative 5. So it's giving you the scientific notation. Some calculators, depending on the calculator, depending on the settings, at some point when it gets to a small enough number, it will show it in scientific notation. But you have to pay attention. If you just look at the 2.76 and give that as the answer, well, you want to think about what makes sense, because there's if it was 2.76 per capita, that would mean there's 2 entire Walgreens locations just for me. There's another 2 entire Walgreens just for you, and like another apartment. The next person, your mom, has 2 entire Walgreens just for her, your sister, your friend, like every single person has 2 entire Walgreens just for them. That clearly doesn't make sense because there's only 188 total in the state. So if that number doesn't make sense, one thing to look for is look at the far right end of the number and see if it has that power of 10. For Michigan, it is going to be 224 divided by 10.1 million, so 10 millions, comma, and then the 1, the other 2 zeros, and then zeros. So putting that in standard form. And this one comes out 0.0000217, so that rounds to 2. So we can see from this that the Indiana number is larger if we start comparing once we get past the zeros, and we see 2.7 versus 2.2. So Indiana has more Walgreens relative to population. If we took all of the Walgreens and gave each of us our own little tiny share of a Walgreens, Indiana's people's share would be a little bit bigger. But if we want a little bit better picture of what this looks like, we can scale this up and say, all right, so if I move those decimal points 5 places, so I get to the non-zero digits. So if I'm going from 0.00000276, if I'm going 5 places, I've essentially have multiplied by 100,000. So I've gone, each place is 1. So this is to 1. If I move the decimal place 1 place, it would be to 10. If I'm moving at 5 places, it's to 100,000. So 100,000 people are combining all of their little tiny pieces of a Walgreens together, and they get 2.76, or somewhere between 2 and 3 Walgreens locations for those 100,000 people. For Michigan, moving that decimal point 5 places, multiplying by the 100,000, however you want to think of that, it's going to be 2.22. And Alex, when you have a question like this, the first step asks you to round to 6 decimal places, 7 decimal places, whatever it is. Then the next step asks you for the per 100,000, per 1,000, per million, whatever it is. It doesn't give you any additional rounding instructions. Then you're going to just keep the digits. You're not going to do any more rounding or less rounding. You're just going to keep the same non-zero digits as you had in your previous answer. So you can see, like, if you had a city of 100,000 people in Indiana, you'd expect it to more likely have 3 Walgreens locations, whereas in Michigan, a same size city would more likely only have 2. And some of them, there's going to be some variation because they're both between 2 and 3, but Michigan is closer to 2, Indiana closer to 3. And then number 3 here, there's 172 gas stations in Fort Wayne and a population of 343,000 people. We want to know how many gas stations are there for every 10,000 people in Fort Wayne. So I take the 172 divided by 343,000. That's going to give me how many gas stations for every 1 person. And that is 0.0005, and it keeps going. But we want to know how many for every 10,000 people. So this is for 1 person. So I'm going to multiply that by 10,000 people. So these 10,000 people combine all their little bits of a gas station, and that moves the decimal point 4 places, and that rounds to a whole number 5. So 5 gas stations for every 10,000 people. Now, if you were really wanting to make this the most meaningful, you would probably say, all right, so how many people for 1 gas station? That makes more sense. That's true, that's a reasonable calculation to make. That is not what you're going to be asked for in Alex. So just be aware of that. But this would be like about 2,000 people to 1 gas station.